Now that we have discussed both the cases of a vector valued function of a scalar variable and a scalar valued functions of a vector variable, we are now in good shape to proceed to the most general case where we will consider a mapping between Euclidean spaces Rn and Rm. So we will fix notation once and for all throughout the rest of this part of the course. E will always denote Rn, F will denote Rm, and n comma m are greater than or equal to 1. N comma m are natural numbers. Okay, and we will always put the Euclidean norm. We will always put the Euclidean norm on E and F. So our objective is to consider an open set U in E and a map F from U to F, and we want to discuss derivatives of such a map. So what should the derivative be of a mapping from an open set in Euclidean space taking values in another Euclidean space? We have already done the hard work of treating the derivative of a scalar valued function of a vector variable as a linear functional. So the definition now that I am about to give will become utterly straightforward. So this is the definition. So as usual, F is from U to F. We say F is differentiable at the point x in U, if we can find a linear map. I'm going to denote this linear map by dfx. This is a linear map from E to F such that you can approximate F in a nice way using this linear map. That is, f of x plus h is just f of x plus dfx acting on the vector h plus E of h, where E is a sublinear function. To be more precise, limit h going to 0 of E of h by norm h is equal to 0. E is defined in some open set that contains 0. So this definition, the way we have been formulating the definition of the derivative, this definition is exactly the same as what we saw some 20 videos ago when we first introduced the derivative in the context of one variable functions taking values in R. The exact same definition works. This part is the affine linear good approximation. This E is the error term. The fact that the error term is small is quantified by the fact that limit h going to 0, E of h by norm h equal to 0. Okay, and similar remarks that we made after the gradient applies. This h has to be chosen so small that x plus h is still in U. We can always do that by shrinking the domain of h to be a suitably small neighborhood of 0. So we can also formulate this definition without involving the error term explicitly by saying that f is differentiable if you can find dfa from E to F such that limit h going to 0 norm of f of a plus h minus f of a minus df a h divided by norm h is equal to 0. So you can formulate the same thing without involving the error function explicitly. In fact, you can even delete the norm. This norm in the numerator is actually not needed. Even without that, the definition is true. You can formulate this in alternate ways. Okay, so immediately let's see an exercise. In the next video, I'm going to explore certain complicated examples of the derivative, but let's see a simple example. Suppose t from e to f is linear. Suppose t from e to f is linear, then show that t is continuous. Okay. Now note E and F are not general vector spaces, they are just shortcuts for Rn and Rm respectively. Any linear map between Rn and Rm is automatically continuous, and the proof is really easy. I want you to show that. Okay. Now we will always put the operator norm on linear mappings. So but we will be treating matrices themselves as elements or vectors. So we will be considering functions defined on matrices and differentiating such functions. And I said that whenever we consider E and F vector spaces which are Rn and Rm, we always put the Euclidean norm. So if you have a matrix M, then it is let's say it's an n cross n matrix. If you have an n cross n matrix, then this is actually, you can treat it as an element of Rn squared in a natural way. Just put the entries of the matrix consecutively as a single vector, you will get an element of Rn squared, and on Rn squared you have the Euclidean norm. But on the matrix M, you can treat M as a map from Rn to Rn because it's an n cross n matrix, and on the matrix M you automatically have an operator norm. In fact, you have this even when you have a matrix which is not a square matrix, a matrix which is a rectangular matrix, an n cross m or an m cross n matrix. So the question arises, are these two related? Well, both norms are going to be equivalent. That's an exercise that we have already seen when we studied non-linear spaces. However, you can say something even better or worse depending on your perspective. So this is part 2 of this exercise. If M is the matrix of T from E to F with respect to some basis, then show that the operator norm of T is less than or equal to the summation over I summation over j mod aij. Okay, so where this M is nothing but aij. So suppose you have a linear transformation from E to F and you represent it as a matrix M with respect to some pair of bases, then the operator norm of T is bounded by this quantity. Okay, so this is going to be very useful in various scenarios. Okay, now finally show that T is differentiable on the whole of E and derivative is itself. This last part is rather trivial, is itself. This will just follow from the way we have formulated the notion of derivative as a best linear approximation. Okay, now I'm going to leave some more facts for you to check. These are easy. Show that if f is differentiable at x, then it is continuous at x. It is continuous at x, and the derivative is unique, You cannot have two linear mappings that simultaneously satisfy the definition of the derivative of f at the point x. Okay, so these proofs go exactly the same as what we did for the derivative of a scalar valued function of a vector variable. Exact same proofs will work. Okay, now in the scalar valued function of a vector variable case, we found out that we can represent the derivative using partial derivatives. A similar thing is true even in this general scenario. Theorem, I'm going to call this the Jacobian matrix of a differentiable map Okay, theorem is as follows. As always, f is from u to f. Okay, and let f be differentiable at x in u. Okay, let b denote the standard basis of E and let C denote the standard basis of F. Okay, now write f as f1 comma dot fn. You can write f in terms of its coordinates. Then each fi is differentiable on u. What are these FIs? These FIs are nothing but scalar valued functions of a vector variable. These FIs are the various components of the function f, each of which would be scalar valued. So there will be m of them, not n of them, because E is Rn and f is Rm. Each fi is differentiable not on u at x, because we assumed differentiability of f only at the point x. So then each fi is differentiable at x, and the matrix dfx, the matrix of the linear transformation with the basis b on the domain side and the basis c on the codomain. So the standard basis is nothing but df1x, then let me just write it in a better way, df2x dot dfnx. Rather, I should not put d because that will be inaccurate. This is gradient of f1x, gradient of f2x dot gradient of fnx. So the various rows of this matrix are going to be gradient of f1, gradient of f2 dot gradient of fnx. Okay, so this matrix is called the Jacobian matrix. Okay, and this Jacobian matrix, which is an m cross n matrix comprising partial derivatives. So when the map f is differentiable, you can write down the matrix quickly with respect to the standard basis by computing the various partial derivatives and putting them as a matrix. So this is the jth partial derivative of the ith function. This is what the ijth entry is going to be. Let's see a proof of this. Let us see a proof of this theorem. All the hard work has actually been done when we prove the corresponding result for the gradient, that the gradient is actually the representation, matrix representation of the derivative map of a scalar valued function of a vector variable. So let's write f of x plus h is equal to f1x, f2x, comma dot fmx plus dfx h plus the sublinear error term. This is just the definition of f being differentiable at the point x. Now dfx is itself a linear map from E to f, which I can write in components as L1 dot 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 Lm, simply because f is an m-dimensional space, so you can just write it as L1 to Lm, where each Li is linear. Because the map dfx is linear, each component must also be linear. Okay, and we can also write this E of h likewise in components as E1h comma dot 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 EMH. So essentially we have just taken the definition and written everything in components. Now because E is sublinear, it is trivial that it follows that each EI is sublinear. This is utterly straightforward. Now putting all this together, what we get is fi of x plus h is nothing but fi of x plus Li of h plus Ei of h. This is just equating all the components. Okay, now it immediately follows that each Li is nothing but dfi at x, which shows that each fi is differentiable, and the fact that the matrix of dfx with respect to the standard basis is going to be just the various gradients of fi's follows from the fact that we have proved earlier that if you have a scalar valued function of a vector variable, then the matrix representation of the derivative map is nothing but the gradient. Putting all this together, we are done. So this was fairly easy because we spent some time proving the easier case of scalar valued functions of a vector variable. Now what about the converse? Suppose I know that each fi is differentiable, then can I get the derivative? Can I show that f is differentiable, and what is its derivative? Well, we can do that by formulating the same proposition, sort of the converse, but this time I'm going to do it independent of these components. Okay, so let f equal to f1 to fm from u to capital F be a function. Then f is differentiable if and only if each fi is differentiable, and in this case the derivative at a given point a is given by the formula v maps to d f1 a e1 just a second, d f1a acting on the vector v e1 plus d f2a acting on the vector v e2 plus dot 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 d fna acting on the vector v en. Okay, so wait a second, this should be em, right, because I want a linear map into the space F, which is an m-dimensional space, where of course where e1 to em is the standard basis of Rm. So this is a formulation that does not involve matrices. It's exactly the same result, including the converse. There is an if and only if condition now. Okay, now one part has already been established as part of the last theorem. So proof that each fi is differentiable, if f is differentiable if f is differentiable was the last theorem, was the previous theorem. Okay, so now we have to prove the converse. We have to assume that each fi is differentiable and prove that the map f itself is differentiable. So we have written f in terms of its components as f1 to fm. Okay, this is same as writing f is f1 e1 plus dot 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 fn fm em. This is exactly the same thing in a different notation. Now we are going to assume that each fi is differentiable and conclude that f is differentiable. So let's consider the difference f of a plus h minus f of a minus the map that we claim is the derivative, that is dfa h e1 plus dot dot dot, actually it's minus dot 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 minus df, so this is df1, so this is dfm a h em. Okay, so we have just written down the map we are interested in, and what we are going to show is that this thing, this what remains is, I'm just going to call it e of h and show that limit h going to 0 e of h by norm h is equal to 0. This will show by the remark that I made just after I defined the derivative, that the function f is differentiable and the candidate derivative that we have is indeed the derivative map. Okay, now how do we know that this is going to be sublinear? Well, observe that by this remark that I made, that f is nothing but this, what we get is we can group the terms together and we will get f1 of a plus h minus minus f1 of a minus df1a h e1 plus dot 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 fm of a plus h minus fm of a minus dfm a h em. Okay, now by the fact that each fi is differentiable, and obviously this is the derivative of each fi by definition, each one of these is sublinear, and it is an easy fact. It's easy to show, it is easy to show that sum of sublinear functions is sublinear. So I'm being a bit vague here because there are these vectors e1 to em. So what exactly do I mean by sum and all that? I am going to leave it to you. These are easy checks. Okay, so this concludes the proof. Okay, what is the net upshot of all this? Well, the net upshot is, if you want to compute the derivative map, there are only two real ways. One is to somehow guess the derivative map and prove that indeed it is the case that this is the derivative map. Alternatively, you can just use these results proved in this video and compute this, which is just essentially one variable calculus. Just compute the various partial derivatives of each component of the map f and put them all in a matrix. That will give you the matrix representation of the derivative map. In many treatments, we don't even introduce linear maps. We directly define the derivative in terms of this Jacobian matrix. Okay, now, but I prefer to do this coordinate independent definition of the derivative map as a linear map, because that fits in with our philosophy that the derivative is supposed to be the best linear approximation of a function. Remember, linear phenomenon are easy. We have spent several generations studying linear phenomenon. We have a huge set of tools that allows us to tackle linear phenomenon. So whenever possible, whenever you are confronted with a nonlinear phenomenon, try to reduce it to a linear case, and the derivative map is the appropriate way to reduce whatever you are studying to the linear case. This concludes this video. This is a course on real analysis, and you have just watched the video on the derivative as a linear map.